Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 8.1 from your textbook, which sort of was setting up all the foundational sort of theoretical background for working with linear differential equations. So in the previous video, we went through and proved a really sort of big result, which was about the solutions to a regular nth order linear homogeneous differential equation. And remember that the main idea of that big theorem was that those solutions actually form a vector space of dimension n. So let's go ahead and make sure right off the bat here that we do a quick follow-up to make sure we really understand what the consequences are of knowing that this solution space is a vector space of dimension n. So let's go ahead and talk about this follow-up right away. So let's consider that we have a regular nth order homogeneous linear differential equation phrased in terms of L of y equals 0, again with L being sort of that general linear differential operator. So let's let y1 through yn be linearly independent solutions to this homogeneous differential equation. Then every solution to this equation can be written as y equals c1y1 plus c2y2 plus cnyn for some scalar c1, c2 through cn. Now, how do we know that this is the case? Well, because of this big theorem here, we know that the solution space is a vector space of dimension n. Here are n functions that are linearly independent. Since they are linearly independent and the amount of vectors matches the dimension, we know that they're going to form a basis. Since they form a basis, that means everything in the vector space, everything in the solution space, every solution can be written in terms of a linear combination of those n linearly independent solutions. That's what this is saying. So in other words, every solution can be phrased as a linear combination of those n linearly independent solutions. We then call this format, where y equals c1y1 plus c2y2 plus cnyn, the general solution to this differential equation. And this ties back into sort of a concept we introduced at the very start of our class when we first were investigating differential equations. We said that there were some differential equations that had general solutions and some did not. But we said that having a general solution is a really big benefit. And we said that in general, linear differential equations do have general solutions. And now we've seen how those general solutions basically come about. They come about by understanding that the solution spaces are vector spaces, and if we can get a basis for that vector space, that basis generates all other solutions, meaning that basis really tells us what the general solution looks like. So this is really a sort of moment tying together some of the things we learned at the very beginning with some of the more recent sort of linear algebra concepts. So what sort of remains then to be done here? Well, obviously, figuring out y1, y2, yn, what are those linearly independent solutions? I mean, just what are the solutions in general? That's going to be sort of the computational part that remains. And we're going to be investigating that in section 8.2 and 8.3. The only sort of theoretical piece that remains, though, is how do we know, if we have a group of n solutions, that they are actually linearly independent? So we're going to investigate that a little bit further. And as you guys might suspect, because these are all functions, understanding their linear independence is going to relate to the Wronskian. So we're going to prove an important theorem with this. So, how to tell if solutions are linearly independent or dependent. So let's first go back to a previous theorem that we introduced, which involved the Wronskian. It was actually when we first defined the Wronskian. So remember, if we have functions y1 through yn, and they're in Cn of r, so they have at least n derivatives, then if there exists a value x0, a point x0, such that the Wronskian evaluated at x0 is not equal to 0, then we know that these functions are linearly independent. And in fact, this was how we defined how to figure out linear independence for functions, right? This is how we basically define linear independence in the functional space. If you guys remember, though, the converse of this was not true in general. In other words, if the Wronskian of a set of functions was uniformly 0, so it was 0 at every possible x sub 0, it didn't tell us anything. It told us it might be linearly independent or it might be linearly dependent, and we actually saw some examples of that. So in general, the converse of this was not true. However, it turns out that the converse of this theorem is true if you know an additional piece of information, specifically that the functions you're examining are solutions to a homogeneous linear differential equation. So we're going to look at this theorem and go ahead and prove it. So this theorem says if you have y1 through yn and they're solutions to a linear homogeneous differential equation, then if there exists a single value such that the Wronskian does equal 0, then these functions are automatically linearly dependent. So if you put these two theorems together, this basically tells you that when you're working with solutions to a linear homogeneous differential equation, the Wronskian tells you everything you need to know. If it's always non-zero, the functions are linearly independent, or it's going to be always equal to 0, then they're going to be linearly dependent. There's only going to be these two options here, because in this special case, we get this converse of this theorem. In general, that's not true when you just pick out random functions, but it is true when we're working with solutions to a linear homogeneous differential equation. So let's go ahead and prove this. So we're going to start by, let's assume that the Wronskian of y1, y2, yn at some x0 is equal to 0. And we're going to consider the system of linear equations. And this is going to look a little bit weird, but this is what we're going to consider here. y1 at x0, c1, plus y2 at x0, c2, plus dot, 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 yn x0, cn equals 0. And then y1 prime x0, c1, plus y2 prime at x0, c2, plus dot, 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 yn prime at x0, cn equals 0. And then all the way down to y1 n minus 1 derivatives evaluated at x1, c1, plus y2 n minus 1 derivatives evaluated at x0 times c2, plus dot, 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 yn n minus 1 derivatives at x0 cn equals 0. Now, I want to just make, this is sort of, it's clear via the notation, but make sure you guys can understand this. These things here are not functions. They're actually these different functions and their derivatives evaluated at a particular value. So these are all actually scalar values. And the unknowns in this case are going to be the C1s, the C2s, and the Cn. So these right now are being treated as our variables. Now, it shouldn't be hard to see that if we phrase this as a matrix equation, we'd be phrasing this as y1 x0, y2 x0, yn x0, then y1 prime x0, y2 prime x0, down to yn prime x0, all the way down to y1 n minus 1 x0, y2 n minus 1 x0, all the way down to yn n minus 1 x0, then times that column vector c1, c2 down to cn equals 0, 0, all the way down to 0. But if you look at this, right, what is the determinant of this? Well, the determinant of this coefficient matrix here, the determinant of that, y1 x0, y2 x0, yn x0, y1 prime x0, y2 prime x0. Right now I'm wondering why I didn't just copy and paste it, but that's okay. Still learning technology, I suppose. There we go. N minus 1 x0, n minus 1 x0. Well, this by definition is what? It's the Wronskian of y1, y2, yn at x0, which is equal to 0. That's our assumption, right? We're assuming that this is the case. So in other words, I built this system of equations so that this would happen. So the determinant of this coefficient matrix is equal to 0, meaning that this coefficient matrix is not invertible, meaning that its rank is not full, meaning that there are non-trivial solutions to this. Now remember, this is a homogeneous, not system of differential equations, but it's a homogeneous system of linear equations. So we always knew it was going to have solutions, c1, c2 equals cn equals 0, but now we've just figured out since this is equal to 0, there's non-trivial solutions. So there's non-trivial solutions exist, right? So let's choose one. Let's choose any non-trivial solution. Let's call it C1 equals A1, C2 equals A2, Cn equals An, where at least one of the A sub k is not equal to 0. So in other words, by choosing a non-trivial solution, at least one of these solutions, A1, A2 through AN, at least one of them is not equal to 0. So in other words, not all the C1, C2 through Cn are equal to 0 here. Okay, so now we have this sort of non-trivial solution. So let's go ahead now, and now we're going to return to discussing the differential equation. So we're going to let u of x, which is going to be a function, be a1, y1 plus a2, y2 plus an, yn. Now, I'm saying u of x just to remind you that now we're going to transition from talking about these systems of linear equations back to talking about functions. I'm not going to be evaluating it at x sub 0 right now. I'm just talking about this in general. Okay? All right. Now, we should be able to sort of see here, clearly, u is a solution to L of y equals 0. How do I know u is a solution to L of y equals 0? Well, because y1, y2 through yn are solutions, and we know that L is a linear operator. So if we did L of a1, y1 plus a2, y2 plus an, yn, the L would distribute onto everything, and we'd be able to show, since every component is a solution, everything would turn into a 0. It would be a solution altogether. We actually have already known this too, because we know that y1, y2, yn, they're all solutions. We know linear combinations of solutions. Everything's a vector space here. Definitely u is a solution to L of y equals 0. Specifically, though, u is a solution to the IVP L of y equals 0, y of x0 equals 0, y prime x0 equals 0, y n minus 1 at x0 equals 0. Now, how do I know that's the case? Well, because that's where I got that a1, a2 through an, right? Those values were chosen so that this system of equations back here all equal 0, meaning that when you evaluate the functions, add them all up, you get 0. When you evaluate the derivatives, add them all up, you get 0, all the way down to doing that for the n minus first derivative. So that basically tells us that u is a solution not only to the differential equation, but to this specific IVP where the function, its derivative, all the way down to its n minus first derivative are all equal to 0. But, well, we also know y equals 0. The 0 function is a solution to this IVP. Right? I mean, certainly y equals 0 is a solution to the homogeneous differential equation, because remember, homogeneous linear differential equations, the solution space is a vector space, so the 0 vector's got to be in there. So that's definitely a solution. And certainly it's also got the property that y equals 0 at any x0 is 0, its derivative is 0, everything's 0. Okay, so it's definitely a solution to the IVP. But remember, solutions to the IVP for a linear differential equation, guaranteed to be unique. So, by the existence and uniqueness theorem, okay, this u of x that we figured out is a solution must be equivalent to 0, because there's only one unique solution. U equals 0. So what does that tell us? Well, that tells us that a1y1 plus a2y2 plus anyn equals 0. But remember, not all the a1, a2 through an are uniformly 0. So we've just figured out a linear combination of y1, y2 through yn that equals 0. So we have a non-trivial linear combination of y1 through yn that equals 0. So what does that mean? So y1 through yn is linearly dependent. Check. Okay, so again, if you want to review this sort of proof, if you look at your textbook, again, they sort of restrict to only looking at a case for 2 functions. We did it in general, so this is a little bit more complex. But really, again, I don't want you guys to get sort of lost in the proof. Really make sure you understand the result. So if we go back here, basically these two things together tell us that when we're working with functions that are solutions to a homogeneous linear differential equation, the Wronskian tells us everything. The Wronskian is either going to be non-zero everywhere and they're linearly independent, or the Wronskian is going to be zero everywhere and be linearly dependent. So the Wronskian, at least when we're working with solutions to a homogeneous linear differential equation, tells us everything we need to know. All right, the last sort of theoretical concern we need to talk about here is how does this apply to non-homogeneous linear differential equations? And it turns out we've got one easy theorem that tells us that. So, theorem. Let's consider the non-homogeneous nth order linear differential equation defined by L of y, that general linear nth order linear differential operator, equals f of x. So this is what's making it non-homogeneous. So we're going to let y sub c, which your book often calls the complementary solution, be a solution to this non-homogeneous linear differential equation. So y of c is a solution to this. We're going to let y1, y2 through yn be a basis for the corresponding homogeneous equation, L of y equals 0. So for the homogeneous one. Then every solution to the non-homogeneous can be written as some linear combination of the basis of the homogeneous solutions plus that one single complementary solution to the non-homogeneous. So in other words, what this is basically telling you guys is that for a non-homogeneous linear differential equation, what you do to generate all the solutions is some linear combination of the homogeneous solutions plus a single solution to the non-homogeneous. So let's go ahead and prove this. So remember, we're letting y sub c be a solution to L of y equals f of x, and we're letting y1 through yn be a basis for solutions to L of y equals 0. We're going to let u be a solution to L of y equals f of x. And we need to show that this u can be phrased like this. Okay, so since L is a solution to this, this means that L of u equals f of x. That is certainly going to be true there, right? That has to be the case here. All right, but now what I want to consider is we also let y sub c be a solution to this. So L of y sub c equals f of x. So what does this tell us about L of u minus y sub c? Well, if we think about that, we know that by definition this is a linear operator. So this is going to mean that this is L of u minus L of y sub c, which is going to be f of x minus f of x, which is going to be 0. So this tells us u minus y sub c is a solution to the homogeneous linear diff EQ. Okay, so u minus y sub c is a solution to the homogeneous one. But remember, y1 through yn is a basis for the homogeneous solution space. So there exists c1 through cn such that u minus y sub c is equal to c1 y1 plus c2 y2 plus cn yn. Because y1 through yn, they form a basis, so any solution to the homogeneous must be able to be writtenable, I suppose, if you want to make up a word, is able to be written in terms of a linear combination of y1, y2 through yn. Now, very simply, move this guy over, and we can see here that any solution u to the non-homogeneous equation is some linear combination of solutions to the homogeneous plus a single solution to the non-homogeneous. So, putting this all together, what this tells you guys for sections 8.2, 8.3, and so on, when we get into the computational side of things, is that for both non-homogeneous and homogeneous, the really bulk of our work is going to boil down to finding these n linearly independent solutions to the homogeneous system. If we're working with the homogeneous, then finding that those n linearly independent solutions is going to be everything. For non-homogeneous, it'll be the first thing that we need to do, and then we'll need to seek out that one single complementary solution. But no matter what, we're always going to be focused at the beginning of finding these y1 through yn, because this result here shows us that these are necessary even when things are non-homogeneous. So in our next video, we'll be moving on into section 8.2 and starting to see how to perform some of those computations.